Hello, AP Calculus students. It's a little late today, but you know, I'm staying late and getting grades done. And finally, this is the last thing I have to do tonight is knock out your homework guide for, this is for 733. We skipped ahead a bit. We did not end up doing 732. In class, we talked about knocking out a lot of these problems. I think what we're going to do is we're going to do A, B, and C off of 7130, and I think that's what we said we would knock off. Everything else looks like it's pretty good to go. So let's jump right ahead and let's look at problem A, which I'm going to do over here in this space. This is the integral of the cosine of x times sine. Forgot how to spell cosine there. This is the cosine of x times the sine squared of x dx. This is a prime candidate for u substitution because sine and cosine are derivatives of each other, which makes them a very common candidate for this kind of thing. So u, let's make that equal to the sine of x. And that means that du will be equal to the cosine of x times dx. And that gives us a perfect one-to-one u substitution. Cosine of x dx, and there's your sine of x right there. Just remember that this is the integral of u squared du, which is going to give you an antiderivative of u to the third power over 3 plus c. The only thing left to do here is to back substitute in the original thing, so it's sine cubed of x over 3 plus c. And there is a properly done u substitution for question A. Question B, you can avoid using u substitution for this one. This is the integral of the negative cosine of 3x minus 2. Times dx. This is question B right there. The first thing that I notice in this problem is the negative. I kind of want to get rid of it because the antiderivative of cosine is just sine. So I want to move it off to the front. How about the negative integral of the cosine of 3x minus 2? You can do this problem with u substitution, but I think this is better done just by kind of laying traps for stuff. The antiderivative of the cosine is the sine. Let's leave this as the negative sine of 3x minus 2 plus c. This is almost correct, but it might be worth thinking, okay, what would the derivative be if we left it alone right now? We would have the negative cosine of 3x minus 2, which is what we want, but we would have this times 3 that would kick out because of the chain rule with 3x minus 2. So we need to deal with that. We need to lay a trap for that times 3. So let's put this whole thing over 3, and that will be the answer that we need. That will account for this 3 that will pop out because of the chain rule. And there you go. That's an antiderivative that you can use for this. I think that will work just nicely. And finally, question C, we have the integral of x to the negative fourth. I'm going to write this one in a couple spots here, x to the negative fourth, times e to the x to the negative third power. I think that's correct. Yeah, times dx. This one looks kind of bizarre. Whenever we start taking exponents to other exponents, I start to nod off a little bit. But I think what we're meant to see here is that these two are definitely derivatives of each other. If we let u equal x to the negative third power, then du will be negative 3 times x to the negative fourth power. And I think that's probably the connection that we want to see. Let's multiply that times dx right there. It's not exactly a one-to-one, but it does match pretty closely. All you'd really need to do here is multiply by negative 1/3 on both sides. I wrote negative twice. Negative 1/3 times du would give you the x to the negative fourth dx that you're looking for. And now you've got a perfect u substitution like that. X to the negative fourth dx is taken care of by negative 1/3 du, and x to the negative third power can be replaced with u. So our integral becomes something like this. We'll have negative 1/3 hanging out in front times the integral of e to the u du. And now it's a lot easier to deal with. The antiderivative of e to the u is just e to the u. So we'll have negative 1/3 times e to the x to the negative third power plus c, just by back substituting in the u from above. And I think that'll do it. If you take the derivative of that, if you really think about it, you will end up getting right back to what's inside of the integrand there in that problem. Pretty cool. The rest of these are all doable. I think we're just skipping them in the interest of time. Question D is, that one's going to require a little bit of thinking as far as the two terms you have, but you basically have too many u substitutions to do there, once for this term and once for this term. Question E, I think, is really simple. It's very similar to B in that all you do is kick the 2 out in front. and then think about the antiderivative of, natural log of 4x. And then question F, I suspect You could do this with u substitution also, I think, but I think this might end up being like an inverse tangent or something like that. But, it's not. It's going to be a natural log. Anyway, I'm not interested in these problems here. I think doing 3 is just enough for this assignment. So let's talk about 7.131, which is going to be kind of a lengthy problem because we're going to locate all of the relative extrema and points of inflection for a function f of x equals 2x to the 5/3 minus 5x to the 4/3. This one's going to take a little bit of time because we got to remember how to do it, but this is very much, it's a review problem for sure, but it's very much a thing you want to keep in the forefront because it's the heart of calculus, is finding the extreme points and the points of inflection using derivatives and second derivatives. So let's get to work over here. This is for problem 7.131. Our original function, f of x, is equal to 2x to the 5/3 power minus 5x to the 4/3 power. So let's talk about extrema first. For relative extrema, we're going to need to think about the first derivative. Because as we've seen before, when your derivative is 0, you have a horizontal tangent, and that's when extrema happen, when your derivative is 0 or undefined. So that's what we're looking for. We're looking for when f prime of x equals 0 or when f prime of x is undefined. So let's take that first derivative and see what we can find. F prime of x. If we bring down 5/3, we'll have 10/3 because it will multiply by 2. And we'll have x to the 2/3 power since 5/3 minus 1 will drop down by, I like to think about subtracting 1 as subtracting 3/3 there. For the next term, 5 times 4/3 is going to be 20/3. And we'll have x to the 1/3 power right there. If we drop down, again, 4/3 by 3/3, you'll get to 1/3. There it is. Here's your second derivative. Like we said, we're looking for places when this equals 0 or when this is undefined. I don't think that it's undefined ever. Let's see. Since we're dealing with cube roots here, the 1/3 power that you see there, those are cube roots. Those can take in anything. If it was an even number on the bottom of these fractions here, we would have to think about negative numbers going in there, but I don't think anything causes this to be undefined. Nothing's being divided, so we don't have to worry about dividing by 0. So let's think about how to solve this for 0. How do we think about when does 0 equal 10/3 x to the 2/3 minus 20/3 times x to the 1/3? I have a couple instincts here. You could start by adding this entire chunk to both sides, and then you could work out algebraically what's going to happen there. That might get a little bit weird. You know what I want to do here? I think what's easiest to do is to factor common factors. We have two terms. Whenever you have a plusy minus problem, which is what's going on here, we have a minus sign. We want to make this into a multiplication problem, because when multiplication problems equal 0, then you can start to see the 2 places or 2 or 3 or 4 places when it could equal 0. So let's think about common factors in this problem. I noticed that both of these, they both have 10/3 as a common factor, so I'm going to pull out 10/3. They also both have x to the 1/3 power. I think this is a common factor we could pull out of both terms. This first term, in order to turn x to the 1/3 into x to the 2/3, all I'd have to do is, let's see, I'd have to multiply it by x to the 1/3 power. I think that would work, because I would add those together if I was going to multiply them, and that would give me, that would give me 2/3. This right there, 20/3 is just, that's going to be 2 minus 2. I believe this is correct. If I do the distribution, I think you'd get right back to where you are now, which is cool. The nice thing here is that now we've got 2 chunks to this problem, and these 2 chunks are being multiplied together, and the answer is 0, which means that one of them has to be 0. Or if, a better way might be to say that if one of them is 0, then the other one becomes 0 because you're multiplying by 0. So let's investigate the possibility of both parts. 10/3 x to the 1/3 power equals 0. And then also let's think about x to the 1/3 minus 2 equals 0. Let me get calculator cam out of the way for a minute here. Let's just solve both these algebraically. The first one is really easy to answer because this is 0 if x is 0. You can do the algebra if you like to, but it turns out that nothing matters. If you multiply both sides by like 3/10 or something, it doesn't matter because you got 0 over here. And then, you're taking the cube root of both sides. Or I guess raising both sides to the third power, which gives you 0 anyway. So that's one place. I mean, that's pretty obvious from the beginning, is that if you plug in 0 for both your x's, you get 0. That's an easy one. The other one over here ends up being 8, because x to the 1/3 power equals positive 2. And then if you raise both sides to the third power, you get 8. 2 to the third power equals 8. So I believe these are the two places where the derivative is 0. Those are the two places where you might have a relative minimum or a maximum. Now, as far as whether it's a minimum or a maximum, there's a couple different ways we could think about that. We could go to the second derivative and talk about concavity. And, you know, since we have to do that for part of this problem anyway, let's think about concavity next. Let's talk about f double prime of x in this problem. F double prime of x might be, usually it's a little more challenging to get than usual, but we'll take our original derivative there. For the first term, 2/3 times 10/3 is going to give you 20/9. 20 over 9. I'm going to get rid of this. Times x to the negative 1/3 power. That's not a fun thing to deal with, but we'll use the calculator to handle it. And the next term, minus, if we do 20/3 times 1/3, that's going to be 20/9 again. That's interesting that it happened in both cases. That's pretty cool, actually. Is x to the negative 2/3 power there. Yeah. I gotta think about that, make sure I'm right. I'm just puzzling over it really quick. I think it looks pretty good. You know, this is not the fun romp that I thought it would be. Did I do that right? 20 times 3. Yeah, I guess that's right. Huh. Interesting. Yeah, I guess that's correct. Okay, so what I'm curious about right now is I want to talk about f double prime of 0, and I want to talk about f double prime of 8. And all I really care about is if they are positive or negative at these points. Because if it's positive, then your graph is concave up, which means that you're at a relative minimum. And if it's negative, it means you're concave down, which means you're at a relative maximum. You know, f double prime of 0 is 0. And I'm not super excited about that because that doesn't really tell us any information about concavity. F double prime of 8, though, I'm just going to crunch that number really quick in calculator cam. Let's see here. If I had 20/9 times 8 to the negative 1/3 power minus, and again, 20/9 times 8 to the negative 2/3 power, I'm going to get a pretty solid positive 0.5 repeating. Now this means that this is concave up, which then means I'm at a relative minimum. Because a concave up graph looks like this and therefore has a minimum. I don't really get any information out of this. This doesn't mean it's neither a minimum nor a maximum. It just means that you can't tell. So I guess in order to tell if it's a relative maximum or minimum, I'm going to have to think about the first derivatives on either side, which I was hoping not to have to do because I feel like that's a lot of work, but I guess we're at that point, aren't we? Let's think about this on a number line here. If we put 0 here and 8 here, let's just think about whether things are increasing or decreasing by thinking about our derivatives here, f prime of x. And all we really care about is positive or negative on either side of this thing. The factored version, I find, is often really helpful here because you can just plug in numbers. Like, let's just plug in -1, for example, and think about what would happen. If we were to plug in -1 into f prime of x, -1 to the 1/3 power would be a negative number. So the first part would be negative. And the second part would be, let's see, -1 to the 1/3 power. I'm just checking to make sure I know what I'm talking about here. That would be -1. And -1 minus 2 is also negative. So this would actually be positive over here. If we plug in a number like, let's say, oh, I don't know, 1, that would be a good fit because it's between 0 and 8. We would have a positive number for the first term and a negative number for the second term. So this would be negative. And that tells me that since this goes from increasing to decreasing, that there is a maximum, or at least a relative maximum, at x equals 0, since it switches from increasing to decreasing. At 8, we kind of already know this is a relative minimum, but I'm just going to confirm really quick. If you plug in any number bigger than 8, a really good choice would be 27, since it's a perfect cube. You get a positive number both in the first and in the second term, which gives you positive numbers here. So that tells us that this is a relative minimum. I'm doing a lot more work than I think I need to from this problem, but I guess I'm doing everything. And that's probably the point of an instructional video, huh? Yeah. Anyway, the only missing piece to this puzzle is we probably want to know the actual coordinates. We know that the maximum happens at 0 and the minimum happens at 8. We probably want to know what the matching coordinate is. And I guess I'm just going to crunch that on the calculator. We're just going to plug those into the original function. So, well, I know that 0, I know that f of 0 is 0. That's an easy one. So I know if I'm making an answer list somewhere, maybe off to the side here, I know that there is a relative maximum at the point 0, 0. F of 8, though, that might take some calculating to do. 2 times 8 to the 5/3 power. I'm plugging this into the original function. Minus 5 times 8 to the 4/3 power. It's going to give us negative 16. And so that'll be the relative minimum of this problem. There we go. Now, as far as points of inflection go, we're looking for places when the second derivative equals 0. Now, we already know, well, if there is going to be a point of inflection, it's not so much about the second derivative equaling 0. It's about the second derivative changing sign. And for example, I suspect what's happening is that it equals 0 there, but it doesn't change sign at 0. So we're probably looking for other places where it equals 0. Again, you could do a lot of algebra here. Let's think about this for a minute. If I was to try to solve this, let me see. If I was going to try to take this maybe down here and think, okay, when does 0 equal 29th x to the negative 1/3 minus 29th x to the negative 2/3? Since the coefficients are the same here, I think we're looking for places where negative x to the negative 2/3 is equal to, or no, it would be positive, because you'd add it, times x to the negative 1/3, which is interesting. I can think of only, let's see, the number 0 obviously works. The only number I can think of that also works there is 1, because 1 to the negative 2/3 power is just going to be 1, and 1 to negative 1/3 power is also 1. I don't think negative 1 works. I think you can take negative 1 to the negative 2/3 power. It's going to be a negative 1. Oh, maybe not. A negative 1 to the negative 1/3 power. Whoops. Negative 1 raised to the negative 1/3 power. Is negative 1. So it only works when x is 1. I guess there's two answers. X is 0 and x equals 1. There's probably better ways to answer this algebraically. Now, 0, I already know, doesn't really tell us any information. So I think 1 is the only other point of inflection. So I think there is a point of inflection at, not 0, at 1, comma, whatever f of 1 is. So I got to go back to the drawing board, f of 1. F of 1 is pretty easy to calculate because it's just going to be 2 minus 5, which is negative 3. Again, looking at the original problem up there, 2 minus 5 is negative 3. So at 1, negative 3. There we go. I believe these are all the answers there. I did not intend for that problem to take 10 minutes, but I kind of knew it would take some time. There's a lot of stuff happening in this problem, stuff that we talked about for 2 or 3 chapters in this class. This is really at the heart of what is calculus, at least in my humble opinion. Calculus A, B at least, with derivatives and second derivatives, maximums, minimums, points of inflection, that kind of thing. Let's move on into 132. Things are going to go a little faster now because we have a lot less work to do on these other problems. All we're doing here in these problems is thinking about what would happen. We don't actually need to do any calculations. We really just kind of got to wrap our head around what's going to happen here. So for question A, we're plugging in infinity to x and also to x squared. Now what's tricky about that is that down here on the bottom, this plus 2, we can just kind of ignore it because in the face of infinity squared, it's not going to do much. It will do something, which is why the answer is going to approach something and not be something, but it doesn't do a whole lot. But what we should see there is that you end up with a square root of x squared, which is effectively approximately equal to x over x. And that's why the answer to this question is 1. Because as the values of x that you plug in get to be larger and larger, they are matching each other on the top and the bottom. So even though they're both infinity on top and bottom, there is kind of a one-to-one relationship, and they will divide out to be 1. Down here in question B, we have the same thing happening. The only difference in this case is that the top of the fraction will be negative infinity. But on the bottom, if you're being careful, when you take negative infinity and square it, it becomes positive infinity. And I guess positive infinity squared. And of course, if you take the square root of that, you get back to regular infinity. So this is actually going to be kind of a pretty solid one-to-one negative infinity over infinity, which is going to equal -1 when all is said and done. Pretty cool. Question C is really interesting. You do see these questions pop up on AP tests every once in a while. It's really, if you ask me, it's an advanced algebra 2 problem. There's really nothing happening here that we really need to worry about as far as AP Calc goes, but I do want to talk about how to handle this. I've seen other teachers call this a fraction action problem, which I think is kind of a corny name, but I mean, it does get the job done. I think this is a lot easier to think about, this problem, if we just get rid of all those nasty fractions on the top. And the best way to do that would be to kind of multiply by the least common multiple of the denominators. So I would love to multiply the top of the fraction by 2x. I'm not allowed to just do that, though. You know, I have to multiply by 1. So what I'm going to do is I'm going to multiply by 2x over 2x. And what that will do, I'll show you what's going to happen here. Oh, first of all, you know, I'm getting kind of ahead of myself. We're talking about the limit as x approaches 2. And the reason why that's a problem right away is if you plug in 2 to x, 2 squared is 4, and 4 minus 4 is 0. So you can't just plug in 2. L'Hopital's rule is a thing you might be thinking about. If you plug in 2, you do get 0 over 0. So you could do this with L'Hopital's rule. Actually, that might be faster. Let's try that. This currently equals 0 over 0, I guess is what I'm saying. So that means that L'Hopital's rule applies. So let's think about this like a derivative. How about that? In this case, the derivative on the top, this would be equal to the limit as x approaches 2 of the derivative over the derivative. So the derivative of 1 over x, that is x to the negative first power. That becomes negative x to the negative second power. And the 1/2 has a derivative of 0, so it doesn't go anywhere. Again, what I'm thinking about there, if I'm explaining everything, 1 over x is actually equal to x to the negative first power. Keep in mind, we're taking the derivative here, not the integral. We've been doing a lot of integrals lately. This is a regular old derivative. -1 times x to the negative second power. And on the bottom, we would have just 2x by itself. What's cool about this is that now the answer is not 0. If you plug in 2, you actually get an answer, and that's what we're looking for. So let's plug in 2. We would have -2 to the negative second power divided by 4. 2 times 2. And this might be easier to think about by writing it a little differently here. First of all, 2 to the negative second power, that's -1 over 2 squared. And how about we multiply by 1/4? Instead of dividing by 4, let's multiply by 1/4. And that's why the answer to this question is 1/16. Because you get 4 times 4 on the bottom, and that's 16. That's better than what I was going to do. I was going to try this. You know, I don't want to get rid of my work. I don't have much room to work with here. Rats. Oh, it would be it'd be negative 1/16. I took a look at it. It'd be negative 1/16. My guys, my friends. If I was to try to not use L'Hopital's rule, here's what would happen. I'd multiply by 2x over 2x. On the top of the fraction, I would get 2 minus x. On the bottom of the fraction, I would have 2x times x squared minus 4. You might be thinking, how does that help? Well, if I rewrite the 2 minus x as negative x plus 2, minus 2. On the bottom, you can factor x squared minus 4 into x minus 2 times x plus 2. And now the x minus 2 cancels out. And you get -1 over 2x times x plus 2. And now you can plug in 2, and you'll get 4 times 4, and 16 is on the bottom. So that's another way to do the same problem. It's debatable which one you think is easier. I think once you learn L'Hopital's rule, I think that's how you should approach all limit problems forever. I think that's a good lesson to learn. I remember we're not going to do C in this problem because it's stupid and dumb and stupid. Let's do 7-133. We're going to compute some derivatives. The first one's really simple. It's going to be a chain rule. The outside function is sine to the 3 power. So we're going to do 3 times the sine squared of x. And then we need to multiply by the derivative of sine of x, which is the cosine of x. And that is all I have to say about that problem. For the second question, I'm going to try to do this in one line, in one step. I think, again, the outside function is the third root, which I want to think about as the something to the 1/3 power. So this is 1/3 times the original inside, 7 plus 4k minus 2k squared, all raised to the negative 2/3 power, like that. And then the only thing left here to do is to multiply by the derivative of the inside part. So let's multiply that times 4 minus 4k. And that is all. I'm sure we could do some simplification here, but who cares? That's it. Let's look at Regina's position along a straight wooden bridge is given by x of t equals log of t, where x is measured in feet and t is measured in seconds. At t equals 1, she passes her friend Angela, who is going the other way, and then at t equals 10, she stops to gaze at the water below. Let's talk about her average velocity over the interval from 0 to 10. We should keep in mind that all the information we're given is the position along a straight wooden bridge, and it's given by x equals log of t. Let's think about this for a minute here. Do we need Angela's information for anything? I'm curious here. Her position is given by x of t equals log of t. X is feet, and t is measured in seconds. At t equals 1, she passes Angela. It's going the way. At t equals 10, she stops, gazes at the water below. So I guess I have no problems. I don't know why Angela's in there, and I don't know why it's important that she passes Angela or that she stops at x equals 10. Let's think about this as maybe on a graph might be a good way to think about this. Let me have some room here. Here's 10, and then we'll have 0. If I go on my calculator really quick and just graph a quick, log of x graph on the window from 0 to 10, it looks kind of like that. Oh, you can't see anything. There you go. Looks kind of like that. I'm even going to change the scale because y never gets to be more than I think 1. There you go. Yeah, it looks something like that. Let's see. Yeah. It's worth noting that she doesn't actually start moving, I guess, until t equals 1. So it looks something like this. Her position along a straight wooden bridge is given by x of t along t. All right. Well, as far as calculating the average velocity goes, what we're going to need to know is that at this point here, basically we should think about. Well, she starts moving, I guess, at 1, 0, and she stops moving at 10, 1. I think that's an important thing to point out here. This is a distance graph, and if we want the average velocity, we're really just calculating the slope of this secant line. I think that's important for this problem, like that. So the average velocity in this case is going to be 1 minus 0 over 10 minus 1, which is 1 over 9. And since this is measured in feet this way and seconds that way, this would be feet per second, like that. That's her average velocity, 1/9 of a foot per second. As far as question B, at what time in the interval was she actually traveling at this average velocity? What we're going to need to do is convert our position function into a velocity function. I'm going to do all this work over here in this little section. Since we are given the x of t, we can find v of t pretty easily. All we have to do is take the derivative of the log base 10 of x, which, do we know how to do? Let me Google that really quick. Derivative. I know that derivatives of non-logs are, that's, oh, you know what? This question's out. Derivatives of any function besides natural log are not on the AP Calculus test, and they're outside of the scope of this class. So it's not too hard to do. But I think question A is reasonable. Actually, you know what? I withdraw. A is good. B is out. That's all I have to say. Okay. Let's talk about 135. I know this. I'm being a little long-winded here. I'm going on 30 minutes, but I'm explaining a little more than I usually do here too, so I'm taking my time. 135, set up an equation to represent the following situation, and be sure to represent your variables. The rate at which a bucket leaks water in centimeters cubed per minute is directly proportional to the amount of water in the bucket at any time. So let's talk about the rate at which the bucket leaks water. We can call that any number of things that we want to call it. Let's say V is volume of what's in there. So the rate at which it's leaking water, the change in volume with respect to time, is directly proportional to, that's going to be K times something, and that would be the amount of volume in the water in the bucket. That would be K times V. Which kind of makes sense. The more volume that's in the bucket, the more water pressure pushing down, the faster it's going to release. Like that. This is a good differential equation for this situation. For the last question here for 7136, we are just going to go onto the calculator and crunch that number. There's nothing more to say about it than that. We could do some clever work here because I noticed that there are some patterns, but honestly, the calculator will be faster than anything else we can do here. We just need to really be careful about typing everything exactly correct. You are going to be required to do this on this test, is to actually, like, sometimes just use a calculator to crunch things out. So 5 to the x minus 2 to the x dx plus the integral from 1 to 400. This is going to take forever for my calculator to calculate. 2 to the x minus 5 to the x dx. You know, could we? This is the kind of problem. Could we do this by hand? Sure. Would we ever do it by hand? Never. Not when, overflow. Well, that makes me think the answer is E, but maybe I just did too much work for the calculator. X minus 2, well, maybe we might be hosed here. Since the calculator can't handle this calculation. That's not good. Can it handle the first part of it? No, it cannot. Okay, how are we going to handle this then? You know, I noticed that it's the integral from 0 to 400. Ooh, I got an idea. Ford's got an idea. All right, I think I know what to do here. Here's what I want to do. I noticed this and this right away. So I want to keep the first integral the same. But I want to change the second one. I want to actually make it negative. I want to factor out a negative. That's what I want to do. The negative integral from 1 to 400 and that allows me to change the order of the integrand, 5 to the x minus 2 to the x. Basically factoring a negative 1 out of this thing, like that, allows me to change the sign of those two terms and then reverse their position. See, what's nice about this is that now I can combine this into one integral. It's integral from 0 to 1 of 5 to the x minus 2 to the x dx. That's a cool problem. I like that a lot. Let's go back to the calculator and let's crunch that number. Just the integral from 0 to 1. Again, we actually totally could do this one by hand. It wouldn't be that hard to do. But we got it right here. Let's set it up. And we got a pretty solid 1.0426, which is B. That's that. That's a cool problem. Your calculator can't help you unless you recognize that pattern going on. Interesting. Okay, you know what? Sub 35. I'll take it, guys. Hey, I will see you tomorrow. You guys are awesome. Keep it up. Yeah, I can't tell you. I'm so proud of how far you've come. You guys are great. I'll see you in the next video.